Section 5.3, part 3 is on the graph of f of x still. So we're going to do increasing, decreasing, concavity, all of those different things. But we're also going to have horizontal asymptotes. Okay? Yes. Okay, it says in a little note, it says L'Hopital's rule is not included in this text in the textbook for this section, but it's very useful when we talk about horizontal asymptotes. So do you guys remember all the limit stuff that you guys did? Any, chapter 1, like limits, you remember that? Actually, it was chapter 2. Yeah, limits. You can actually solve a lot of limit problems using L'Hopital's rule. So this is something that is not necessarily Calc AB. It is on the BC exam, but we don't say it's on the AB exam, but you can use it all over the AB exam. So instead of doing some limit rules that we did before, you can use L'Hopital's rule. L'Hopital, not La Hospital. L'Hopital. So, all right, remember when we computed limits, we sometimes plugged in values. Remember when you plug things in, you would get 0 over 0 or infinity over infinity, and you'd be like, wait, what's the answer? And then you had to do some kind of factoring trick or something to find out what the limit was. Same thing, like we're going to do something else to find those limits. So if I have like the limit as x goes to 1 of x squared minus 1 over x minus 1, if I plug in 1, I get 0 over 0. So if that happens, I can use L'Hopital's rule. So in order to use L'Hopital's rule, it needs to be an indeterminate form. So when it is something like 0 over 0, infinity over infinity, those are the main things for L'Hopital's rule. But if it's in another indeterminate form, a lot of times you can change it around so it's in one of those two forms. So like, I don't know, like 0 to an infinity, infinity minus infinity, like what are those different things? Like, I don't know. So these are all other indeterminate forms. So if you can get it in the form 0 over 0 or infinity over infinity, we do something that seems very, very strange. You just take the derivative of the numerator, and then you take the derivative of the denominator. That's it. So your limit of something that looks like this, so limit as x goes to c of some function over another function, as long as if you plug in and you get 0 over 0 or infinity over infinity, what we do is we just take the derivative of the numerator and the derivative of the denominator, and then whatever that's equal to, that's your limit. Okay. So it says the limit as x goes to c of f of x over g of x, it's equal to that same L. And it's true for left-hand and right-hand limits as well. Okay, so let's try some practice with L'Hopital's rule. It's kind of strange at first. So the first one, I have the limit as x goes to 0. I have 1 minus cosine of x all over sine of x. So if I plug in 0, I get 1 minus 1. Right, cosine of 0 is 1. All over sine of 0 is 0. So I get 0 over 0, right? Okay, so when that happens, we use L'Hopital's. This poor guy's name. I don't know how many people called him hospital. All right, I think that is actually how you say hospital in French. So, all right, anyway, so what I do is I do like a little equal sign and I put an H over it, so I remember that I use L'Hopital's rule. And I take the derivative of the numerator and denominator. Don't forget to write your limit. So limit as x goes to 0. The derivative of 1 minus cosine of x is 0 minus a negative sine of x, right? All over the derivative of sine of x is cosine of x. So we end up getting sine of x over cosine of x. Yeah, tangent. Can you plug in 0 for that? Like, what do you get when you plug in 0? Numerator, sine of 0 is, cosine of 0 is 1. 0 over 1 is 0. The answer is 0. Okay, the next one. So if you plug in 2, you get 0 on top. You get 4 minus 6 plus 2, you get 0 on the bottom. So you have 0 over 0. So if that happens, you can use L'Hopital's rule. So I'm going to take the derivative of the numerator and the derivative of the denominator. So you get 2x over 2x minus 3. So don't just like think, oh, whenever I'm taking the derivative of a quotient, I can just take the derivative of the numerator and denominator. You would need quotient rule. Right? This is only for limits that you are allowed to do this. This makes sense. I'm not taking the derivative of the limit. I'm taking the derivative of each individual piece. Okay, so I'm going to have Now I can plug in a 2, right? So if I plug in a 2, I get 4 over 4 minus 3. So I get 4. So that's your answer. So a little bit faster sometimes than the other method. No, so the question is, when do you need to stop writing limit? As soon as you're able to plug things in, you don't need to write limit anymore. Okay? So like at this point, when I plugged things in, I didn't need to write a limit in front because I had already plugged in the value. Okay, so this next one, limit as x goes to 0 of sine of x over x. This is the one that I told you to memorize. Do you guys remember what this one is? Let's see. So you can always get it with L'Hopital's rule if you're confused. If you're like, ooh, is that the one that's 1 or is that the one that's 0? What is it? So if I plug in 0, I do get 0 over 0. So I'm going to do the limit as x goes to 0. Derivative of sine is cosine. Derivative of x is 1. So what do we get? 1. So Nia, you were right. Whoa. Second guessed yourself. All right, so this next one is an infinity over infinity. Natural log is really weird. Natural log is like the slowest thing that goes to infinity ever. Because if you do the graph of natural log, here's what it looks like. This goes to infinity, but it goes so slow. So everybody get out your calculators. Do like natural log and then put like 5, 0, 0, 0, 0, 0, 0. Like do a whole bunch of zeros. Right, like maybe 10 zeros.
On the graph.
Just like on the main screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hit enter. I got 24. With 10 zeros. So natural log goes super slow to infinity, but it does go to infinity. All right, so based on that, I can kind of tell what this next one's going to do without even doing L'Hopital's rule, because I know that x goes to infinity so much faster than natural log of x goes. So think about that. If the top is like going to be a huge number, if I did like a table of values and I put in 5 with 10 zeros at the end of it, right? The top is going to be really huge. The bottom is like, 24. It's going to go to infinity. Does that make sense? So I can kind of tell, and that's a good way to like logic through a lot of the infinity ones. But in this case, let's go ahead and do it. So if I plug in infinity, I do get infinity over infinity. But calculus is really the study of infinities, right? Which one's bigger? So I'm going to do L'Hopital's rule. So I do the limit as x goes to infinity. I have the derivative of the top is 1. The derivative of the bottom is 1 over x. So I simplify. So I'm not doing L'Hopital's rule again or anything. I'm just rewriting. I'm saying this is 1 divided by 1 over x. So now you can clearly see that it goes to infinity. All right, the next one. So I have the limit as x goes to pi from the left. So in this one, if I plug in pi, sine of pi is 0. 1 minus cosine of pi is -1. What do I get? Do I need L'Hopital's rule on this one? No, because my answer is 0. Ah, tricky, tricky. So be careful. You should always do that step where you plug in, because if it's not 0 over 0, if you do L'Hopital's rule, you're going to get it wrong. Okay, so this next one, this is one that's 0 over 0. Do you guys see why I did both problems? Okay, so I have, this one is 0 over 0. So I'm going to do L'Hopital's rule. So I'm going to say the limit as x goes to pi from the left. I'm going to do the derivative of sine is cosine. The derivative of 1 plus cosine is negative sine. So now I'm ready to try plugging in pi. If I plug in pi, I get cosine of pi, which is -1. And then I have minus sine of pi, which is 0. And I'm like, what's that? I can't do L'Hopital's rule again because it's not 0 over 0. So I need to think about it. You can't. I gave you a direction. I gave you that direction for a reason. Okay, this graph. It approaches 0. Nope. This graph is negative cotangent. Okay, many of you guys probably don't remember what negative cotangent looks like. Do you guys know what shape it looks like? It's not the u's. That was cosecant and, or that was cosecant and secant. It's kind of like the x to the third. Do you remember that? So you can graph it if you need to. This wouldn't be one that I think your AP test would put on there. But think about where cotangent is undefined. Well, it's undefined whenever sine is equal to 0. So sine equals 0 at 0, pi, 2 pi, and so on. So at 0, pi, 2 pi, and so on. So I'm going to have vertical asymptotes at all those places. Okay. And then I need to decide, like Lydia was saying, it's like this kind of thing, or it could be like this kind of thing. We need to figure out which one it is. Okay. So let's try some different things. Okay, so let's try pi over 2. If you try pi over 2, you get cosine of pi over 2 over negative sine of pi over 2, which is, cosine of pi over 2 is 0, so you get 0. So it's right there, which kind of makes sense. Okay, what if you try something smaller than it, like pi over 4? Cosine of pi over 4 over negative sine of pi over 4. You get square root of 2 over 2, square root of 2 over 2, but you have a negative on the bottom, so it's negative 1. Okay, what if you do 3 pi over 4? What are you going to get? Close, but cosine of 3 pi over 4 and sine of 3 pi over 4 are opposite in sign, right? Cosine is negative, sine is positive, so you get a positive 1. That helps you to see that it's doing like this wiggle like this. Like it's going like that. Do you guys remember this from pre-calc? Did you do any of this? No. You didn't grab? It's like fun stuff. So like, no. All right, so our question is, as we approach pi from the left side, okay, what am I going towards? Right here. Positive infinity, so this answer is infinity. What if I said pi from the right side? 0. Then it's down here, negative infinity. So that's why the direction on that one mattered, because it was, you were determining between positive and negative infinity. Okay, guys, what are you doing over there? Okay, so next up. So I have a limit as x goes to 0 of e to the x minus 1 all over x squared. All right, so let's try to plug in 0. So I'm going to have e to the 0 minus 1 all over 0, which is e to the 0 is 1. 1 minus 1, 0. So I get 0 over 0. So I can use L'Hopital's rule. So I say the limit as x goes to 0. And I take the derivative. So e to the x is itself e to the x minus 1 all over 2x. And then I try it again. So if I plug in 0, e to the 0 is 1 minus 1, which is 0, all over 0. L'Hopital's rule again. So I get e to the x over 2. So what's my answer? 1/2. That's right.
Wait, if e to the x is plug in 0.
E to the x.
1 minus 1.
Yeah, so 1 minus 1 is 0
Yeah.
over 0. So since you have 0 over 0, you go again.
We should do one where it's like 20 minutes.
Oh, yeah. That's what I put on the test for sure.
Yeah.
No, I mean 20 L'Hopital's rule. You guys would kill me. I'd have like hate notes.
Nope.
Okay, you walk out. All right, this one. So I have the limit as x goes to 0. I have natural log of 1 plus 7x. So if I plug in 0, do you guys see it's natural log of 1? What's natural log of 1? 0. So I have 0 over 0. So I do my L'Hopital's rule. So I get the limit as x goes to 0. I have the derivative of natural log of 1 plus 7x. It's 1 over 1 plus 7x times 7. Good. Don't forget your chain. Divided by 1. So I'll clean it up a little bit. So it's the limit as x goes to 0 of 7 over 1 plus 7x. Now can you plug in 0 and get an answer? Yep. So your answer is 7 over 1 plus 0, which is 7. All right, Bob. You asked. I listened.
So, like,
20 times. Yeah. Not quite 20, but you'll have to do it a couple times on this one. All right, so if you plug in 0, tangent of 0 is 0, minus 0, all over 0. So what's the most number of times that I'm going to have to do this? 3, 4? Let's think about it. So I start out with x cubed. So when I do L'Hopital's rule one time, I get something with x squared. So that's one time. When I do it again, I get something with x the first. When I do it again, I get something with just a number. So I'm going to have to do it 3 times. Okay? Yeah, it's lovely. All right, so L'Hopital's rule. So I get the limit as x goes to 0. Derivative of tangent is secant squared minus 1 over 3x squared. Then I plug in 0, secant of 0, that's 1 over cosine, which 1 over cosine of 0 is 1. 1 over 1 minus 1 is 0. So I still have 0 to 0. Right, secant of x is 1 over cosine of x. So if I plug in 0, I have 1 over cosine of 0, which is 1 over 1, so 1. So I have 1 minus 1, and then I have 0 on the bottom. You with me?
Yeah.
So I'll do it again.
So you have to do 1 over cosine.
So now we have secant squared. Think about that. That's like secant x squared. Help her out. Derivative of secant x is secant x tangent x. And the minus 1 goes away, right? Derivative of minus 1 is 0. All over 6x. Oh, man. Or 6. I always do that with, like, 3x squared.
I think you told us.
I always do, like, 9x or something. Or 2x cubed, that's what it is. I always do 8. I don't know why.
I do that all the time.
It's the simple things. You like keep track of all the hard things. Like poor Hannah the other day for homework, she wrote for her name, she wrote, instead of Hannah, she wrote homework.
When you know.
The little things in life, but it's just too complicated. Oh man. Okay, so this next one, let's try to simplify a little bit. I don't really know how to make this much easier. Let's go with like cosines and sines. Can we do that?
Yeah.
Kind of goes back to the trig identities. Do you guys remember trig identities? So we have 2 over, now secant is 1 over cosine, so I'm going to put a cosine on the bottom. And then I'm going to have a cosine on the bottom. And then tangent is sine over cosine, so I'm going to have a cosine on the bottom and a sine on top. And then I'm going to have 6x. Do you see anything that I did there? Or do I need to do that again?
We're good.
And I'm going to reduce out and have a 3.
I don't get it. Because secant is 1 over.
Okay, so let me write out all the steps. So I have 2, 1 over cosine, 1 over cosine, sine over cosine, sine of x over cosine, and then divided by 6x. So what happens is, like this is like 2 over 1, so you get 2 sine of x on top, and then you get 3 cosines, right, cosine cubed, but then you have divided by 6x. So it goes down on the bottom with it. So it goes down there. Is there what?
So then, wait.
Did it change to what? We haven't done that yet. We haven't done the derivative yet. We're just trying to clean it up a little bit. Still pretty gross though, right? So it's still... So here's what we have. We have 3 cosine of x, or 3x cosine of x cubed. Ugh.
Okay.
Yeah, but you got the product and the chain on the bottom, right? Gotta hate that. All right, L'Hopital, this is the last time though, I think. Maybe I've messed it up since I lost my 6x on the bottom. It would have been one more time if I just went from here. All right, what do we get? So we get derivative of the top is... Is it still 0 over 0 when I plug in? Yeah, sine of 0 is 0, and then the x makes it 0. Okay, so we have cosine of x. So this will be the last time because we have cosine of x on the top, right? We can plug in there. And then I have product rule. So I have first times derivative of the second. Plus derivative of the first times the second normal. Lovely. Yeah, the good thing about this is this whole part right here goes away. This is all 0 when you plug in 0. The top, right, cosine of 0 is 1 over. The bottom is 3. 1/3 is your answer. I will not do that to you on the test. I won't. The AP test won't do it to you either because the L'Hopital's rule isn't really on the test, air quotes. So you can use it all over the test. That's why I teach it. Oh, man. All right. Is it break time? Are you guys ready for break? All right. All right. All right, so it says, notice L'Hopital's rule does not cover all of the indeterminate forms. So all of the things where you're like, I don't know if this does not exist. I don't know what this is. I can't determine it. So you also have to consider other things, like if you have infinity minus infinity, or 0 to the 0, or 1 to infinity, or one of these different things. So your goal is to try to get these into the form 0 over 0 or infinity over infinity. Oops, I don't know what happened there. 0 over 0 or infinity over infinity. And then when it's in one of those forms, you can use L'Hopital's rule. So the very first one I have, limit as x goes to infinity of x squared times e to the negative x. Yes? Because there's different sizes of infinities. That's kind of like the x over natural log of x thing we had. Like, you can't just say it's infinity divided by infinity is 1 because, like, this one goes really slow, but this one goes really fast. Okay. Right? So it ended up being infinity. So you have to consider, like, which one's bigger, I guess. Okay, so on this first one, I have x squared times e to the negative x. So think about if you plug in a really, really huge number. I mean, just think about, like, 5 million, you know, or even 500, so I can write it. If you had 500 squared times e to the negative 500, right? I don't know what that is because that is in the form, like, if this was a larger number, obviously not 500, but it would be like infinity times, what would the second one be?
Negative.
Not negative infinity. 1 over infinity, which would be, yes, 0. So that's in the form infinity times 0. Okay, so this is an indeterminate form. We don't know what infinity times 0 is. One of them could be going much faster than the other one. So the one going to infinity could be going really fast. The one going to 0 could be going really slow. Yeah. Yeah. So we try to get it into one of those forms, the 0 over 0 or infinity to over infinity. So what's the easiest thing to do? Could you guys see, like, what you could do with e to the negative x? Okay. All right, if I have e to the negative x, I'm going to rewrite it as 1 over e to the x. So I'm going to have the limit as x goes to infinity of, is that x squared? X squared over e to the x. It's like a negative exponent you can bring to the opposite location. Okay, now it's in the form infinity over infinity. Did you guys see it? Okay. So we just have to kind of determine which one's going faster. So since this is infinity over infinity, we're going to use L'Hopital's rule. Okay. So I'm going to do my little equal sign, limit as x goes to infinity, derivative of the top is 2x, the derivative of the bottom is e to the x. So I get infinity over infinity again. Dang it. Gotta go one more time. Don't you hate that? But it's only one more time because now this becomes 2 on top. Okay. So my answer is 2 over infinity. What is that?
0.
0. Yep. All right, so same idea on this next one. So I have limit as x goes to 0 from the positive direction, and I have x times natural log of x. Okay, I can't take the natural log of 0. But you can try things from the positive direction. Like if I do natural log of 0.000001, I get a negative 16. If I do natural log of point and I do lots of zeros, I'm hitting 0 a lot. 1, negative 52. So it's one of those things where it's going to a form of infinity. It's going to negative infinity, but it's going really slow. Okay, so this one goes to negative infinity. And this one goes to 0. So I have 0 times negative infinity. So I don't know if it's 0. I don't know if it's negative infinity. I don't know what it is. Okay. So I need to get it in one of those two forms. Okay. So if I could get it to be 0 over 0, that would be good. Or infinity over infinity. Or even, you can even actually do negative infinity over positive infinity. That works as well. Okay. So I'm going to use that trick that I used here, like the 1 over thing, like it was 1 over e to the x. I'm going to use that here as well, but it's going to be really weird. Like x can be written as 1 over x. You're like, what? I'm trying to get it to be a fraction, so we got to do something weird. So I'm going to have the limit as x goes to 0 from the right of natural log of x on top divided by 1 over x. Right? It's kind of like over x to the negative 1. If you brought it to the bottom and made it negative. All right, now do you guys see that it's a negative infinity divided by a positive infinity? So it's in that form. The signs don't matter. Okay? So now go for L'Hopital's rule. So I have the limit as x goes to 0 from the right, 1 over x divided by, this was on your derivatives drill, do you guys know it now? Derivative of 1 over x? Negative x to negative 2, so it's negative 1 over x squared. So what is this? It's 1 over x divided by negative 1 over x squared, which is 1 over x times x squared over negative 1. So what do we get? Which is, right, it's negative x, yep. So now as I go towards 0, what am I going to get? 0, that's it. Okay, so what's the point of this? Why am I doing all of this? Okay, the reason is because L'Hopital's rule can be used for horizontal asymptotes. So on your homework, you guys have horizontal asymptotes. This is where the notes end for this section. So when I say something like the limit as x goes to infinity, what I'm saying is what's happening on the end of my graph. In this case, it was going towards 0. It's a horizontal asymptote of 0. Does that make sense? Now, some graphs have 2 horizontal asymptotes. Terrible. What does that mean? 2 horizontal asymptotes. For instance, there are graphs that look like this. It has 2. Okay. I think inverse tangent is like that. Inverse tangent. Okay, it would have 2 horizontal asymptotes. So you need to consider what's happening as your function goes towards infinity and as it goes towards negative infinity. And on your homework, I don't care how you find those horizontal asymptotes. For instance, if I give you y equals x squared minus 3 over 2x squared minus 1, you better believe that I hope you know how to find the horizontal asymptote. Do you guys know how to find that horizontal asymptote?
Yeah.
1/2. That's the shortcut method. You guys know that that's 1/2. Right?
Yeah.
That's fine. You can do that on the homework. If you see it right away and you're like, oh, it's 1/2, right, 1/2. But if you don't see it, you have to do the limit. And you might have to use L'Hopital's rule. Okay? So I have a whole section that's on L'Hopital's rule, and then I have a little section that's on horizontal asymptotes. All right.
So, wait, I confused how the rule